Hello, welcome to From My Living Room to High Vacuum series, Season 1, Episode 2. I want to briefly explain laser-induced damage threshold tests explained in ISO 21254 standard before diving into the coating materials and techniques. There are two expressions and two popular and trusted techniques for LIDT testing. If you use pulsed lasers, maximum laser fluence with zero damage probability is expressed in joule per centimeter square. If you have a continuous laser, maximum laser intensity is expressed in watt per centimeter square. Now we know how to express the values. Let's talk about the calculating these values using experimental data. There are two popular techniques, one-on-one and S01. LIDARIS is one of the best and most passionate companies specializing in LIDT tests. I'll use their demonstrations to explain these two popular techniques very well. Let's start with one-on-one test. Imagine a matrix on a lens 5x5 for simplicity. In this case, you have 25 sides to test. In one-on-one test, you send your laser beam to each side only once for a certain time and power. For each column, each side is exposed a constant power of laser beam, and for the next columns, you larger the power. For each column, you inspect the sides and calculate the damage probability, simply dividing the damaged sides by the total irradiated sides. Finally, you fit the data and calculate the LIDT value. Another popular technique, or maybe the most popular one, is S01. In this technique, you irradiate each side multiple times. S represents the number of shots, pulses. For example, if you irradiate each side for 1,000,000 times, you can call 10 to the 6 on one test. In this technique, you increase the power and number of pulses until you observe a damage in each test site. Then you determine your LIDT value using the irradiation versus number of laser pulses data. There are different ways to detect imaged sites, such as differential interference contrast microscopy or using scattered light detector technology. As it is stated, it is extrapolated data, extrapolated probability that damage will be zero up to the specified value determined at the end of the test. But that doesn't mean that there will be no damage below this value. It's just a probability. And never forget, if you do the test on a witness sample, this may not reflect the real result of your optics. Failure may come from both glass itself or coating. Polishing materials, liquids, and techniques strongly affects LIDT of your optics, as well as coating materials and deposition methods. It's always a good idea to buy optics from factories who knows high LIDT polishing and coating techniques very well. It is not as straightforward as it is seen. There are lots of details and tricks about testing. Even the spot size during testing may cause a wrong conclusion, although it satisfies ISO standard. Around 200 microns or higher spot size is a good idea to not overestimating your LIDT. You can scale LIDT value for different wavelengths and pulse lengths with simple formulas. It will work well if the values are not too far apart. You can use these simple formulas. For high LIDT coating, we typically use hafnium oxide as a high index material and silicon oxide as a low index. To reach high LIDT values, using hafnium metal as the starting material and using reactive evaporation techniques under oxygen partial pressure is preferred. Preconditioning, oxidizing hafnium metal before evaporation, is critical both for LIDT and UV coating applications. You can also buy melted hafnium inserts ready to use from the suppliers, if you don't have time or experienced operators, engineers. Here are some step-by-step suggestions to prepare hafnium oxide from hafnium metal. Step 1. Set your dissociated oxygen MFC 30 to 50 SSEM or maximum to fill the chamber with good amount of oxygen and wait 20-30 minutes to reach a steady state. Step 2. Slowly increase the E-beam power to melt the hafnium. At a certain value, you'll see that your chamber pressure starts to drop, since hafnium will suck the oxygen in the chamber and start to oxidize. Increase the power slightly over the maximum power that you use in your process to keep the evaporation rate at your target value. Step 3. Wait at least 10 minutes to vent the chamber. If you do everything correctly, you'll see that your hafnium will look like melted silver and you'll be successful. During evaporation, closely look at the chamber pressure to decide the right amount of oxygen to give during evaporation, because hafnium will suck a lot of oxygen in comparison to other oxide and suboxide materials to reach desired stoichiometry. It's a good idea to feed the chamber with both oxygen from plasma source and dissociated oxygen from the chamber itself. If you don't get enough densification using only oxygen in your plasma or ion source, increase the argon to oxygen ratio by keeping your chamber pressure at a certain level for the sweet spot between the ion current density and ion energy. Depending on the plasma source, keep your rate 2 or 3 angstrom per second to get dense and absorption-free layers. If you still have an absorption, it means you did something wrong, or maybe your chamber is too dirty, but you can bake your optics in a suitable oven at 300 to 380 Celsius degrees for 4 to 12 hours depending on your film stack. In this way, you can lower absorption and increase your transmission with post-processing techniques. While designing your coating, E-field should be taken into account. OTF Studio has a feature to calculate and optimize E-field for you. There are 3 golden rules. 1. Stay away from the interface between the high index and low index materials. 2. Put the highest peaks to the lower index layers, because typically lower index materials have higher band gaps. It means higher LIDT. 3. For high index materials, hafnium oxide is better than tantalum pentoxide, and tantalum pentoxide is better than titanium oxide. This is all connected to the band gap itself. Due to production techniques, hafnium includes zirconium impurities. You can find hafnium or hafnium oxide with less than 0.2% and less than 0.7% zirconium composition at 99.95% purity levels on the market. Less zirconium content is better for UV coating, since it will be less absorption, and higher ones are preferred for high LIDT coating. If you have experienced technicians, using hafnium metal is always a good idea in comparison to hafnium oxide granules, which are sublimating and growing over your crucible, and it may be stuck if you use and rotate your multiple pocket E-gun. But hafnium oxide granules are useful for simple AR coatings, since you can directly sublimate without melting and preconditioning. This will save you some time. And this is the end of the second episode. If you have any questions, feel free to comment under this post or send me a message. Have a great absorption-free and high LIDT coatings. Bye bye.